In the vast darkness of space, there are events so powerful that they can erase the very stars themselves. These are supernovae, cosmic detonations that unleash more energy in a single instant than our sun will produce in its entire lifetime. For most living things, the birth of such an event marks the end of everything they have ever known. Yet deep in the cosmic archives of light and dust, there is a story that suggests survival is possible. A story of matter, energy, and perhaps life, persisting in the aftermath of what should have been certain annihilation. Before we explore this hidden resilience of the universe, if you are fascinated by the untold realities of our cosmos and want to journey deeper into its wonders, make sure you stay with us until the end of this exploration, where we piece together clues from the edge of destruction. A supernova begins with a star far more massive than the Sun, living a much shorter but infinitely more volatile life. Stars spend most of their existence fusing hydrogen into helium in their cores. This process creates the pressure needed to balance gravity's constant inward pull. But massive stars burn through their hydrogen quickly. They move on to fuse heavier elements, helium to carbon, carbon to oxygen, and so on, building an onion-like structure inside. At the very core, the star eventually begins fusing silicon into iron, and iron, unlike lighter elements, does not release energy when fused. The engine stalls. In a fraction of a second, the delicate balance between outward radiation pressure and inward gravitational collapse is lost. The core collapses under its own immense weight. When this happens, the core can shrink from thousands of kilometers across to just a few tens of kilometers in less than a heartbeat. The temperatures soar 2 billions of degrees. The collapse rebounds in an immense shockwave, blasting the outer layers of the star into space at a significant fraction of the speed of light. The result is a supernova explosion that can briefly outshine an entire galaxy. The debris races outward, carrying with it the heavy elements forged in the star's dying moments: gold, uranium, iodine, and countless other atoms essential for life. For any nearby worlds, this is devastation beyond imagining. The radiation is lethal, the shockwave obliterates atmospheres, and the stellar debris can strip planets down to barren rock. At distances of several light years, a supernova can still have dangerous effects, disrupting climates and damaging DNA on planetary surfaces. And yet, astronomers studying the remnants of ancient supernovae have found evidence that certain planetary systems may persist, and in rare cases, life's building blocks may even survive. The remnants of supernovae, known as supernova remnants, ORS and RS, are immense clouds of expanding gas and dust. They are hot, turbulent, and bathed in high-energy radiation. Over tens of thousands of years, these remnants cool and spread out. Within them, astronomers have found complex molecules, carbon chains, amino acid precursors, and other organic compounds. How can such fragile molecules exist in a region that was once the heart of unimaginable destruction? The answer lies in the physics of dust grains and molecular shielding. When a supernova explodes, much of the dust in the surrounding space is vaporized, but as the shockwave sweeps through the interstellar medium, it also compresses and heats regions rich in gas. In the cooling aftermath, new dust can form. Tiny particles, often just microns across, act as shields, protecting delicate molecules from intense radiation. Observations using telescopes like ALMA and the James Webb Space Telescope have revealed surprisingly high quantities of such dust in the remains of supernovae SN 1987A. Some of these dust grains contain the same isotopic fingerprints found in meteorites here on Earth, suggesting that material from ancient supernovae became part of our solar system's original building blocks. The survival of dust and molecules in a supernova remnant is more than a chemical curiosity. It is a direct link between stellar death and planetary birth. Every element in our bodies heavier than helium was created in such an explosion. Calcium in our bones, iron in our blood, phosphorus in our DNA, all were forged in the heart of a massive star and scattered across the galaxy by a cataclysm. The resilience of these atoms means that even in the face of cosmic annihilation, the seeds for new worlds and new life can emerge. But can entire planetary systems survive a nearby supernova? Computer simulations suggest that planets in very close orbits will be obliterated, consumed by the expanding outer layers of the dying star. However, planets in wide orbits, tens to hundreds of astronomical units away, might endure. If their atmospheres are stripped, they may be left as frozen, airless worlds, but their solid bodies remain intact. Over millions of years, these surviving planets can accrete material from the surrounding debris, potentially developing new atmospheres from the enriched gases in the supernova remnant. Some astronomers have identified pulsar planets, worlds orbiting neutron stars, the dense remnants left behind after a supernova. These planets are exotic, their skies dominated by the radiation from a collapsed core just 20 kilometers across, but with a mass greater than our Sun.